Hi everyone, I'm Zheng Qin, a PhD student from Xi'an University. In this video, we will introduce our work. MotionTrack, learning robust short-term and long-term motions for multi-object tracking. I will give a short introduction to this paper below. The main challenge of multi-object tracking lies in maintaining a continuous trajectory for each target. Existing methods often learn reliable motion patterns to match the same target between adjacent frames and discriminative appearance features to re-identify the lost targets after a long period. However, the reliability of motion prediction and the discriminability of appearances can be easily hurt by dense crowds and extreme occlusions in the tracking process. In this paper, we propose a simple yet effective multi-object tracker, that is, MotionTrack, which learns robust short-term and long-term motions in a unified framework to associate trajectories from a short to long range. Extensive experimental results on MOT-17 and MOT-20 datasets demonstrate the superiority of our approach in challenging scenarios, and it achieves state-of-the-art performances at various MOT metrics. Though great progress has been made in the past few years, MOT still remains a challenging task due to the dynamic environment, such as dense crowds and extreme occlusions, in the tracking scenario. As the figure A in this slide, pedestrians do not move independently in this situation. They will be affected by their surrounding neighbors to avoid collisions, which will make their motion patterns hard to learn in practice. As for the extremely occlusion, pedestrians are easily occluded by fixed facilities for a long period, such as billboard and sunshade, in which the dynamic environment will make them undergone a large appearance variation. This paper is dedicated to solving these two problems in the tracking process. To solve these, we propose a simple yet effective object tracker, that is MotionTrack, to address the short-range and long-range association problems in MOT. In particular, our MotionTrack follows the tracking by detection paradigm, in which both interaction-aware and history trajectory-based motions are learned to associate trajectories from a short to long range. Our MotionTrack mainly executes two steps for each video frame. Step 1. Short-range association. Modeling the inter-tracklet interaction to obtain more accurate predictions and the short-range tracking results. Step 2. Long-range association. Re-identifying lost tracklets based on the history trajectory and unmatched detections, and then compensating the trajectory during occlusion. To deal with the short-range association problem, we design a novel interaction module to model all interactions between targets, which can predict their complex motions to avoid collisions. The interaction module uses an asymmetric adjacency matrix to represent the interaction between targets, and obtains the prediction after the information fusion by a graph convolution network. Thanks to the captured target interaction, those short-term occluded targets can be successfully tracked in dense crowds. To deal with the long-range association problem, we design a novel refined module based on the history trajectory of each target. It can effectively re-identify the lost targets through two steps: correlation calculation and error compensation. For the lost tracklets and the unmatched detections, the correlation calculation step takes the features of history trajectories and current detections as input, and computes a correlation matrix to represent the possibility that they are associated. Afterward, the error compensation step is further taken to revise the occluded trajectories. Extensive experiments on two benchmark datasets, MOT-17 and MOT-20, demonstrate that our proposed MotionTrack outperforms the previous state-of-the-art methods. Our MotionTrack outperforms the state-of-the-art methods in most key metrics, that is, ranks first for metrics IDF1, HODA, assay, data, IDs, frag, and ranks second for MODA. Consequently, it produces more accurate associations and vastly outperforms the second performance tracker in metrics reflecting the association ability, that is, +2, 0 IDF1 and +3, 1 ASSA. For the IDs metric, we are 40% less than the second one, which shows the strong ability of our association component. The ablation study in the figure reflects the role of the two modules we propose. See the result of motion model. We compare the prediction accuracy, in which we take the average IOU of all targets to count the total IOU score. The results show that the introduction of interaction yields more accurate predictions than the traditional Kalman filter. Meanwhile, steady improvements in IDF1 and ASSA indicate that interaction module improves prediction accuracy and leads to stronger association capability. As shown in comparison with other methods for handling occlusions, We compare the classical approach with our method in terms of its ability to handle long-term occlusion. The results show that the first two methods cause dramatic performance decreases due to a large number of incorrect associations, while our approach method achieves a consistent improvement in dealing the long-term occlusion. Specifically, in order to assess the severe congestion and obscuration problems we are trying to address, we filtered these scenarios to target. The improvement in samples of different difficulties illustrates the effectiveness of our method in solving dense crowds and extreme occlusion. We provide video demos, where different colored boxes represent different identities, and red bolded boxes represent the location during occlusion after the long-term refind. For the cases in our demo video, red bolded, almost all other methods fail to track them. Tracklets before and after crowds or occlusion have different identities. Thanks for your attention.